mass than our Sun. It began about 13 billion years ago and is still under construction. It's our galaxy, the Milky Way.
The Milky Way galaxy is an extremely active place. It's like a construction project. There's things going on all the time. And you have old stars die and get torn down, and then that material gets used to build brand new stars.
In the midst of this work zone lies our little solar system and a whole lot more.
I suppose the best way to think of the Milky Way galaxy is our family of stars. These are the stars that we travel through the universe with in a clump, all orbiting a common center.
Within its far-reaching spiral arms lie clues to where we started and how it will all end. On a clear summer night, the stars of the Milky Way unfurl like a shimmering banner across the sky. Ancient Egyptians saw this river of stars as a pathway to the afterlife, but the Greeks were the first to name it. The Milky Way comes from the word galakos, which is Greek for milk. And though we once believed we lived at the center of the universe, we now know that we don't even live in the center of our own galaxy.
When we look up into the night sky and we see this milky swath of stars that we call the Milky Way, what we're actually seeing is a spiral arm of the galaxy that's closer to the center of the galaxy than we are. We can't really see the center of the galaxy from here, but what we can see is one of the spiral arms that's a few thousand light years closer to the center than we are.
As we gaze at the Milky Way from our earthbound position, it's like looking at the edge of a coin. We get no sense of the galaxy's real shape.
If, however, you look at a galaxy from the top down, it's a disk, remember, and it's like looking at a frisbee from the top down. You can see its full glory. Even though it's thin, you don't see how thin it is, but you see its full structure.
You can make the analogy of the Milky Way as being very much like a city. There's a central region, there's big buildings, there's a lot of action in the middle. And that's certainly true of our galaxy. Then you move out to the suburbs, where life is a little bit more comfortable, a little more relaxing. It's a better place to raise a family.
This is where we reside. Our solar system is among the Milky Way's spiral arms, 26,000 light years from the bustling center. Our galaxy is so large that it takes Earth more than 200 million years to make one lap.
The sun's located in what would be just an average neighborhood around the city center. But again, if you're standing in the middle of this neighborhood, you don't really know what the neighborhood on the opposite side of the city looks like, because you can't see it directly.
As we move outward, beyond the suburbs, the population becomes more sparse.
And yeah, you've even got sort of the boondocks. In our galaxy, you've got the halo, where you have very old stars in sort of wide orbits around the galaxy.
The galactic sprawl doesn't stop at the Milky Way's loose and undefined halo. It reaches far beyond our neighborhood and out to a group of galaxies called the local group.
If you think of the Milky Way galaxy as a city like Los Angeles, then you can think of these as counties all within the state of California. And together, this local group makes up the entire state.
Besides our huge Milky Way and the even larger Andromeda galaxy, the local group consists of close to 50 smaller galaxies, the closest of which are roughly 40,000 light years away.
There are two relatively nearby dwarf galaxies, the large and small clouds of Magellan that orbit our Milky Way galaxy and are easily seen in the southern hemisphere. They're small little galaxies. But our local group has several dozen such galaxies sort of wandering around inside it. The big galaxies are the minority.
One advantage of actually being in the outer edges of our galaxy, we have a clear view of outside of our Milky Way. We're able to see the rest of the universe, our neighboring galaxies and galaxy clusters beyond our own local group of galaxies.
Inside the Milky Way's halo lie massive globular clusters.
Globular clusters are densely packed regions of stars that are all of similar composition. These are like the ethnic neighborhoods of the Milky Way galaxy.
Indeed, these globular clusters formed when the galaxy was very young. They are among the first stars to have formed. Some globular clusters are 12 or 13 billion years old. They contain 100,000 or even 1,000,000 stars.
Globular clusters, almost as old as the universe itself, gave us the first clue to our place in the galaxy.
We saw these globular clusters in the sky, but their center was somewhere far away from us. And that was one of our first measurements of where the middle of the galaxy should be. They weren't orbiting around us, but around an area somewhere about 27,000 light years away.
We can never get far enough away from our own galaxy to actually see it. But by looking at other galaxies and comparing what we know about our own galaxy, we've got a pretty good picture of the Milky Way.
The very first time we saw galaxies through telescopes, we didn't even know they were galaxies. We thought they were just nebulae in our own galaxy, and we were just amazed by the beautiful spiral shape. So it was sort of natural for astronomers to classify galaxies according to their shape, what we see.
Astronomers recognize 4 basic galactic shapes. Elliptical, built of old stars and which doesn't spin. Lenticular, consisting of a bulge and a disk and little or no new star formation. Irregular, which has no real shape at all, like the Magellanic Clouds in our own local group. And spiral, which includes our Milky Way. It's a pinwheel of young and old stars spinning gracefully through space.
A long time ago, people thought that maybe an elliptical galaxy eventually collapses down into a spiral. Or maybe eventually spirals all come together and form an elliptical. And it was sort of hard to figure out exactly what the sequence is. One thing we know is that elliptical galaxies tend to be very large.
Centaurus A, a misshapen elliptical galaxy about 13 million light years away, suggests why elliptical galaxies get so big.
There's a lot of evidence that there's a spiral galaxy in there somewhere that got absorbed by a larger galaxy. So right now it's possible that these really big elliptical galaxies we see may be the mergers of several spirals and other types of galaxies.
Our Milky Way isn't in danger of being absorbed anytime soon. But the heart of our spiral galaxy has revealed a secret of its own.
Only recently we discovered that the Milky Way is not a classic spiral, but a barred spiral. There's a bar of stars going through the center, and the spiral arms sort of attach off from that bar.
Spanning 27,000 light years, it's the most popular bar in the galaxy. 30 million stars gravitate to it.
The bar of our galaxy is a natural result of gravity, the mutual gravitational interactions of the individual stars that form the disk of our galaxy and the bulge of our galaxy. It causes sometimes the stars to sort of bunch up into this bar configuration.
Surrounding the middle of the Milky Way is a huge central bulge. It's mostly composed of stars between 10 and 11 billion years old. The size of the bulge is linked to the Milky Way's most gripping feature of all, a supermassive black hole. Though it would easily fit in the space between the Earth and our Sun, it's 4 million times more massive than our Sun.
Now that sounds like a lot, but other galaxies have central black holes which extend up to 1 billion times the mass of our Sun. So, whereas we call our black hole at the center of our Milky Way a supermassive black hole, among supermassive black holes, it's kind of a runt.
Black holes can't be seen directly because light can't escape them. Astronomers have located galactic ground zero through a radio source in the constellation Sagittarius, known as Sagittarius A star. It's creating quite a stir.
The black hole in the middle of our galaxy is spinning, and it appears to be spinning at a rate of about 1 spin per 11 minutes.
As it spins, central region stars caught in its gravity get swept along for the ride, orbiting it at about 3 million miles per hour. The black hole affects the central region the most. But we can't feel its tug on Earth since we orbit the galaxy far away from the center. The colossal forces at the galaxy's heart are negated by the Milky Way's unimaginable size.
To me, the name Milky Way sounds like something kind of comforting, sweet, a candy bar, that sort of thing. But the Milky Way galaxy is a monster. It is incredibly huge. So when you think about how vast our solar system is, the fact that it takes years for the fastest spacecraft to get out to Saturn or Jupiter, if the entire solar system were the size of a CD, the Earth would be comparable to the Milky Way. That's huge. That's absolutely mind-blowing, and it never ceases to amaze me.
And the amazement goes on and on. The galaxy's bustle and commotion may be concentrated in the center, but the spectacular spiral arms have action of their own. It's here that stellar neighborhoods are being built and stars are being born. This is our galaxy. It's a lot to take in, and we're just beginning to probe its depths. Our suburban location makes it difficult to get the big picture, and the hazy clouds of cosmic dust only block our view. Even the most powerful optical telescope can't pierce the darkness. So if we want to learn more about the Milky Way, we need to look beyond what our eyes can see. For all its vastness and empty space, the Milky Way is tremendously active and populated with some astonishing phenomena. Star clusters, nebulas, blazing invaders from other galaxies. Technology is making us rethink old beliefs and is showing us things we've never even considered before.
We have a mission and liftoff. T plus 15 seconds, sending the New Horizons spacecraft on its way to the very edge of our solar system.
We live on a dusty planet in a dusty galaxy in a dusty universe. Empty space isn't so empty. Optical telescopes can see only as far as the nearest dust cloud, which isn't far at all.
Most of our galaxy is invisible to us, however, and that's because the galaxy is full of dust clouds, if you will. And these dust clouds block the light from most of the stars in our galaxy. It's surprising how little of the light from our rather luminous Milky Way galaxy reaches us. The reason for that is simply because the dust blocks it.
But visible light is just a small sliver of the energy spectrum, and radio waves rush in where visible light beams fear to tread.
On a foggy day, you might not be able to see very far at visible wavelengths, which your eye can see, but you can still listen to your radio or watch your TV.
The ability of radio waves to penetrate space dust is crucial to the study of the stars, but that use was discovered by accident. In 1933, Carl Jansky, an engineer at Bell Labs in New Jersey, built an antenna to track down the source of static on transatlantic telephone lines. He was surprised to discover the interference was raining down from the center of our galaxy, the constellation Sagittarius. It took several decades for scientists to realize that Jansky was onto something. Celestial bodies emit electromagnetic radiation, and thus radio astronomy was born. But radio waves were just the beginning.
Because the human eye can't see all the light that's available, we have to resort to technology. And one of the best ways of seeing the universe in a very different way is with an infrared camera.
An infrared camera sees only the wavelengths generated by heat, then converts it to something the human eye can see.
There actually is no visible light at all that passes through this lens. This lens only lets heat light through. And then you can see what everything looks like in infrared light.
3, 2, main engine start.
In 2003, the Spitzer Space Telescope, equipped with a battery of infrared cameras, was launched into space.
Evolution of our universe.
Its mission is to explore some of the youngest stars and farthest galaxies in the universe.
The instruments that Spitzer has on it are actually many times, millions of times more sensitive than these cameras. But they're basically the same thing.
This camera doesn't peer into the heavens, but is used by firefighters to save lives right here on Earth. The camera can see through a smoke-filled room to read the body heat from an unconscious or immobilized victim. The same technology has enabled astronomer Susan Stolevy to see 26,000 light-years away, visualizing the center of the galaxy as never before.
This high-resolution mosaic was assembled from roughly 12,000 individual images taken from the Spitzer Space Telescope. Even though that sounds like a lot of data, and it is, it only took about 16 hours of telescope time. This particular region of the galactic center spans an area of the sky that's equivalent to 4 full moons in one direction and 3 full moons in the other.
That's the equivalent of 900 light-years across by 700 light-years high. A small fraction of what's out there to see, but a phenomenal achievement nonetheless.
Just a few decades ago, the galactic center was not a subject of study because you couldn't see it. Visually, nothing gets through. Only one light wave in a trillion can penetrate the dust. But if you go into the infrared or use radio astronomy or X-ray astronomy, you can see what's going on there.
Different wavelengths of the electromagnetic spectrum can reveal different aspects of the galaxy because they penetrate celestial objects differently. Radio waves have the lowest energy or longest wavelength, but most celestial objects emit them. Then comes infrared, visible light, ultraviolet. High-energy X-rays with wavelengths about the size of an atom are emitted by black holes and supernovas. The highest energy gamma rays come from the collision or decay of subatomic particles, like when stars explode at billions of degrees. Together, these waves give astronomers a more complete picture of the activity and shape of our galaxy. Many, if not all, of the wavelengths are needed to study the cosmos. The various wavelengths of the electromagnetic spectrum are similar to the strings on a violin.
In music, many wavelengths of sound are used to communicate a musical idea. This piece has a very large range from a low note to a high note. If we were to restrict ourselves to the visible light spectrum, it's almost as if we were only to hear 2 notes in the middle of that piece.
Using alternate wavelengths, the more we look, the more we're discovering.
Just recently, we've discovered that there are 2 small galaxies colliding with the Milky Way right now. And the only reason we didn't know they were there is because there was so much dust in the disk of our galaxy, we couldn't see them. We're living inside this cloud, and it's something we're not aware of. But with infrared light, you can cut through that dust. And the minute we turned infrared telescopes to the sky, we saw these little galaxies up there coming right at us.
From our cockeyed position in the Milky Way, it's difficult to gauge what our galaxy really looks like. Radio and optical astronomy give us a glimpse of its features, but to get the big picture, we need to look outward.
So the way we gain some understanding of our own galaxy is first of all by looking at other galaxies and seeing what they look like, and seeing things in other galaxies that correspond to things that we see in our own galaxy. like clouds of gas that are kind of lined up along what looks like a spiral arm. You know, we can see parts of spiral arms in our own galaxy, and we figure that they're all connected, kind of like the spiral arms of other galaxies that we can see from the outside.
We know that the Milky Way's 4 main spiral arms swing out from the downtown center like wide streets. From the inside out, they're named Norma, Scutum Crux, Sagittarius, and Perseus. If the arms are the galaxy's suburbs, then our solar system lives on a quiet dead-end street between Sagittarius and Perseus on what's called the Orion Spur. All the stars in the Milky Way add up to a community of about 200 to 400 billion, and they're on the move.
We are orbiting around the galaxy. We change our position. So far, we think the sun has always been about the same distance away from the center, but we've been in and out of pretty much every spiral arm that there is.
The spirals are called density waves, areas where the stars and gas get pushed together. As the density waves spiral around, the billions of stars ride over and through them.
When you think about watching the Tour de France and you see all of these bicycles, they're all moving forward. Sometimes they kind of clump up around one bicyclist, and sometimes they're stretched out. That's sort of what the spiral arms are like, that the stars are going around like the bicyclists, sometimes in clumpy areas and sometimes in more spread out areas, but they keep going around the center.
Stars don't usually travel alone. While giant globular clusters populate the galaxy's halo, the galactic disk has open or galactic clusters. These bundles of young stars are barely held together by their mutual gravity.
Now, open cluster implies that the stars are actually free to go. It is open. So this is a cluster usually of many stars that have formed together, all from one of these giant clouds of dust and gas. Over time, they're going to move away from each other, distribute themselves around the galaxy.
Astronomers have counted about 20,000 open clusters in the galaxy. The Pleiades is the one found nearest to the Earth. It formed 100 million years ago and will be around at least twice that long before the galaxy's spiral arms tear it apart. Closer to home, our own sun, orbiting in solitude, may have once been part of an open cluster star that struck out on its own. The sun, the star clusters, our own planet, in fact, the entire galaxy and the universe beyond are built of dust and gases. These particles that now block our view are what got us here in the first place. And the star-making machinery is still cranking. Nothing beats the spectacle of a glorious sunset. But we owe it all to dust and gas.
The setting sun appears yellow, orange, or even red for 2 reasons. First of all, the molecules of air in the atmosphere are scattering the violet, blue, and green light out of our line of sight, leaving the yellows, oranges, and reds to reach our eyes. And second of all, particles like dust or smoke or smog in the atmosphere absorb blue light more than they do red light.
Even the grandeur of a blue sky is really an optical illusion.
Why is the sky blue? There's nothing blue about the gases of our atmosphere. But as sunlight comes through our atmosphere, the shorter wavelengths, the blue light, gets scattered more than the longer wavelengths do. So if you look at any particular part of the sky, you're more likely to see blue light being scattered towards your eye.
Space is dark because there aren't enough gas or dust particles to reflect the light of a billion stars. And though space may be a vacuum, it's not perfect. The galactic disk, the largest portion of the Milky Way, owes about 15% of its mass to dust and gas. Gas clouds can span hundreds or even thousands of light years, providing the raw material that fires the galaxy. These regions of cosmic dust and gas are called nebulae, and they produce effects rivaling anything seen on Earth. A good example is the Orion Nebula in the constellation Orion. This region is active with stellar formation, which makes the gas around the stars glow.
It's literally fluorescing in response to the light coming out of the massive stars that are near the nebula. And this nebula literally glows and can be seen. You can see it with your naked eye.
When you see the Orion Nebula, in a real way, those are baby pictures for us. 5 billion years ago, we were in a glowing hot nebula, and the sun and the planets were forming together under the influence of gravity.
Orion, which contains hot stars ionizing its gases with ultraviolet light, is called a diffuse or emission nebula. Astronomers classify two other categories of nebulae.
Some nebulae are what are called reflection nebulae. They're simply, the dust in these nebulae is simply reflecting the starlight from the bright star nearby.
The Witchhead Nebula is an example of a reflection nebula, borrowing light from the star Rigel. Reflection nebulae appear blue for the same reason our sky does. Blue light is more easily reflected than red. And last, there are dark nebulae, like the Horsehead. When low-mass stars like our Sun die, they form another kind of nebula called a planetary nebula. These dim, short-lived nebulae, like the Cat's Eye Nebula, spew elements back into the galaxy. These may become raw materials for new suns and new planets. Just as dying stars spew out clouds of dust and gas can come together to form stars.
At a construction site, you have old buildings being torn down and new buildings going up. And it's very much the same in the Milky Way galaxy. You have old stars explode and they cast out new material, raw material, gas and dust that can be used to form new stars.
Nebulae are the galaxy's recycling centers, where old becomes new again.
Recycling is not just a good idea here on Earth. It's a natural cosmic law. In fact, our own bodies are made out of recycled material from earlier generations of stars that had dispersed material into the interstellar medium before our own solar system formed.
Each generation of stars creates heavier elements, which become the ingredients for everything in the universe. Most of the galaxy's hot young stars get built in the Milky Way's spiral arms.
As gas clouds orbit the center of the galaxy, like the stars do, they get squeezed as they go through a spiral arm. Remember, a spiral arm is simply a wave in the pattern of stars. And because stars are denser there, the gas clouds that orbit through it tend to get compressed. That compression allows gravity to get a hold of that gas and cause it to collapse to form stars more readily there than anywhere else.
Stars often die in the spiral arms because they are formed here more frequently, victims of their own enormous mass.
The more massive stars are extremely powerful, extremely luminous, and to be that luminous, they have to use up their energy source very quickly. So massive stars live only short lives, and they are thus found in or near their birthplaces, the spiral arms, because they simply don't have enough time to wander away from the places where they were born.
Although we can anticipate the future of some stars, it's often difficult to learn their history. But new techniques are revealing new secrets about a well-studied star in the Milky Way called Mira A.
Mira has actually been a favorite star of astronomers for 400 years. It's a very easily visible star in the night sky.
Recently, the Galax spacecraft, the Galaxy Evolution Explorer, photographed Mira in invisible ultraviolet light and revealed that it's leaving a trail 13 light years long behind it.
We think that's actually caused by the fact that as the star plows through the gas heats up in a bow shock, very much like waves breaking up against a boat, and then that streams out into a wake of hot material. You're actually looking at Myra acting very much like a boat plowing through the water. When you look at how fast Myra is going right now, about 291,000 miles an hour, and you do the calculations, that long tail is its path for the last 30,000 years. We can't predict exactly where the sun will go in its orbit around the Milky Way. There's all kinds of things it could interact with. But here we have the history of one star. We know this is the path it took. And that'll help us model how the galaxy works and how all the stars move around the middle of the galaxy.
Within the Milky Way's suburban spiral arms, young stars enjoy plenty of space to move around. As we move into the galactic bulge, conditions get much more crowded and urban.
Closest star to the sun is a little more than 4 light years away. And when we look up into the night sky, even on a perfectly clear night with no lights around, you can't see more than about 2,000 or 3,000 stars. But if our planet was down in the middle of the galaxy, there would be 1,000,000 stars in the night sky as bright as the brightest star that we've ever seen in our sky. And it would be so bright that, in fact, it wouldn't be nighttime, it would be daytime all the time.
Life as we know it would be completely different. So what do we owe our position to? Scientists believe that gravity has a lot to do with it. Gravity is the power that drives the galaxy, and at the galaxy's center churns the engine it feeds.
Galaxies are like a city in that they are ever-changing and you're constantly being rebuilt and reinvigorated. There's no question that the Milky Way a few billion years ago looked a lot different than it does today. It probably was smaller, it probably didn't have the beautiful spiral shape that we see today.
As things collapse under gravity, you tend to naturally form a disk. You'll notice there are disks everywhere. Our solar system is a disk, our galaxy is a disk. So the stars all start rotating in the same direction.
Just as in a city, not all the stars in the galaxy are natives. Some stars born beyond the Milky Way settle here and begin to make their mark.
But then, if another galaxy comes by, the gravity affects the way the stars move, and this may initiate the spiral arms. So, in fact, our spiral shape may be some evidence that the Milky Way is composed of more than one small galaxies that came together a long time ago.
Historically, the center of the galaxy has been an impenetrable mystery until we developed X-ray vision.
One of the first ways we really identified where the exact center of the galaxy was with an X-ray telescope. Well, the X-rays were able to pass through all of the dust and gas in the disk of our galaxy. And so even though we can't really see this bright center to the galaxy, in X-rays there's this giant glowing hot source right in the middle.
The X-ray emitter, Sagittarius A star, is associated with the supermassive black hole in the Milky Way's center. By definition, a black hole doesn't allow light or even X-rays to escape. The radiation comes from gas caught in its gravity, spun and heated to millions of degrees.
They're moving at extremely high velocities. For example, the more extreme cases that we've been able to observe, the stars are moving as they pass by the black hole at a speed of 10,000 kilometers per second.
That's like going around the world in 4 seconds.
And we're talking about a whole star moving at that speed.
When we watch stars orbiting the very center of our galaxy, it's obvious that there's some sort of invisible monster there. They're orbiting around a giant mass, and the orbits of the stars imply that there's about 3 to 4 million times the mass of the sun in the very center of our galaxy. We're not sure which came first, the galaxy or the black hole, but we know that it's there, and it's tremendous.
For all its power and weirdness, the supermassive black hole is pretty typical for a galaxy the size of the Milky Way.
Other spiral galaxies and big elliptical galaxies also seem to have supermassive black holes in their middle, ranging from 1 million times the mass of our sun up to several billion times the mass of our sun.
The stars surrounding the black hole are ancient. Many are red giants, hundreds of times bigger than our sun. The galactic center is crowded with them, like an urban downtown, crowded with people. And stars, like people, can be pushy.
Most stars in the galactic center simply just keep orbiting the central black hole. But in the galactic center, there's so many stars packed so close together that stars are constantly nudging each other a little bit gravitationally. And their orbits are being perturbed, changed a little bit.
A bumped star can get stripped of its atmosphere, leaving just its orbiting core. Or rarely, it can tumble into the black hole and vanish. But something else is happening around the black hole. This turbulent, dangerous neighborhood is also a stellar nursery.
The stars that we're observing moving fastest around the black hole are the young stars that have very recently formed. And it's something we call the paradox of youth, because it's hard to imagine how to form these massive young stars in the presence of a black hole, and yet there they are.
Recently, astronomers discovered that not all stars caught in the black hole's grip are doomed to stay there. A few managed to break away and see the universe. Barreling through the universe at 1.5 million miles per hour, hypervelocity stars are the escapees of the galaxy.
And what's interesting about hypervelocity stars is the only way to explain their extreme velocities is that they're ejected by a supermassive black hole.
For a star to go ballistic takes a very specific set of circumstances. And in fact, it requires 2 stars. Most of the stars you see in the sky are not single stars, but pairs or binary stars. They orbit around each other, linked by gravity's embrace. But a star pair in the galactic center might get jostled by surrounding stars and stray too close to the black hole.
When that happens, the moment that the gravitational pull of the black hole exceeds the gravity that's binding the 2 stars together, the pair of stars is broken apart. One of the stars will be captured by the black hole, usually into a very tight orbit around the black hole. And the other star will then gain all the energy of that system and be ejected with this incredible velocity.
If the galaxy were a city, where most of the stars would be cars or pedestrians, a high-velocity star would be more like an airplane or a high-speed train rushing out of the country.
If you were on a high-velocity star, the ride would be quite amazing. The sky would be covered with stars as bright as the full moon in every direction. But that view would quickly change. Because the high-velocity star moves so quickly out of the galaxy, the stars would appear fewer and fewer in the night sky.
The galaxy is constantly in motion, like a giant wheel or a sprawling metropolis. In the heart of town, the supermassive black hole's gravity whips stars around in an orbit of around 11 minutes. Where the Earth sits, 2/3 of the way out on a spiral arm, we traverse the Milky Way once every 250 million years. Our solar system has been around the block only 18 times since it formed. The Milky Way's incomprehensible size makes it easy to forget it's just one small part of an expanding universe.
When people hear about the expanding universe, a common misconception is that everything is expanding. And in fact, I'm not expanding right now. My atoms are the same size. My cells are the same size. The Earth is not getting farther away from the sun.
The expansion of the universe only applies to celestial objects that aren't bound together by gravity. Since the planets within the Milky Way have stronger gravitational pulls than the expanding forces outside our galaxy, the expansion of the universe doesn't affect our solar system.
Our own Milky Way, a spiral galaxy, is on a collision course with another spiral galaxy, the largest spiral near us, and that is the Andromeda Galaxy. We think that in maybe 3 or 4 billion years, our two galaxies may merge together. It'll be very interesting to see what happens.
What probably won't happen is a collision of stars. Even though both galaxies contain billions of stars, the space between them is enormous. They will gravitationally interact, changing their direction and motion. Eventually, the merged spirals will settle down to become an elliptical galaxy.
Essentially, all of the several dozen galaxies in our local group will be part of one supergalaxy. And then, gradually, that supergalaxy will start losing stars because of gravitational interactions among the stars within that galaxy. Some will get flung away into intergalactic space.
When it first formed, the Milky Way built stars at a rapid pace, using raw materials that were ejected in space from the Big Bang. As the galaxy aged, the star production slowed down from a few hundred a year to about 4 to 6 new stars each year today.
Over time, the Milky Way galaxy has changed dramatically, and we don't know exactly what it looked like long ago, but probably early on there was a lot more gas and dust and probably fewer stars, and you had a lot of very large, very massive stars that would have formed early on. And then these early stars exploded fantastically and spat out new material, heavier metals that could be used to form smaller second generation and then third generation stars.
Some younger galaxies are still enjoying that kind of building boom.
We can see some galaxies where the rate of star formation is very high compared to our galaxy. Those are called starburst galaxies. The rate of star formation there can be anywhere from 10 to 100 times what it is now in our galaxy.
With every generation, star production slows down. And the Milky Way has been in business for 13 billion years.
One of the reasons that the rate of star formation in our galaxy has changed over time, going from a very high rate to the current modest rate of star formation, is because the gas is being used up. Gas is used up to form stars, and we're running out of gas, literally.
Eventually, over trillions of years, star formation will stop completely. The Great Galactic Construction Project will shut down. And one by one, the twinkling stars will fade away.